Make sure it's red. ECGR 4101, 5101, Embedded Systems, lecture number 3. Our continuation of chapter 3 information, chapter 2 information. My hope is to get through this by the end of the day. How many of you read chapter 2? How many of you did not read chapter 2? Oh, some of you are actually honest, all right? One thing I need to actually point out to you is sometimes I'll announce things in class and sometimes I won't, because you're responsible for going to my webpage and keeping up with stuff. And our webpage has been pointed out to you before. So if we go on the readings, I said read book chapter number 2. Of course, I didn't update this for Monday today and then Wednesday, so I will do that as soon as I go back to my office. By the way, the YouTube video of the 2011 class will be here. I may post 2012 versions of the class as well, so you can keep up with it. You should have read chapter number 2. Read chapter number, look over chapter number 3 before you look at the videos that I'm going to put online or have available for you to look at online. So the main concept that I want to continue talking about today is associated with using a microcontroller to communicate. If you remember from our last class, the main concept that I went over is this concept right here. What if I have, on this case, here's a port 4 as an input, a port D as an output, and what I did here is I set up a direction register to say every single bit of port 4 is going to be 0. Every single bit of port D is going to be output. That's a 1 in that position. So what you will need to do is to ensure that you set it up correctly. So in our example, what I'd like to point out is hardware-wise, what would this look like? Well, we said port D was what? Output, right? So port D is an output. And what is our simplest output device you can even think of? LED. So we're going to have D.0, and D.0 will actually look like a LED with some sort of resistor tied to ground. By the way, is it preferred to do this? Or is it preferred to do this? Does it make a difference?
Yes.
All right, what's the difference?
LED would be more responsive in the first one than the second.
More responsive. Do you agree with that?
No.
Yeah, I don't think I agree with that either, but if you could show me an example of that, I'll give you a free trip to the prize closet.
Sometimes what happens is the voltage level switching on, since it is a diode.
So you're talking about the diode voltage
Yes.
that comes out of the pin. Well, one thing to mention too about the output pin of a microcontroller, how much current does it does it source?
Which one?
See the data.
Depends on the controller.
It depends on the microcontroller. Usually it's really low. Something like 5 milliamps is not unusual. All right? So from this respect, does it usually make a difference? Yeah. You know what? I've asked this question to people who design these, and I've got both answers, believe it or not. So I'm going to go with, right now, it doesn't matter if you can give me a website or documentation that says which way you should do it. I'd like to see that in a trip to the prize closet, all right? So, either one of these in my book is acceptable. And at least when you do this, the current that you should source will be 5 milliamps or less. So can you drive a transistor? I'm sorry, can you drive a motor directly with this?
No.
No. Can you drive a transistor?
Yes.
Most likely, yes. You can drive the base of a transistor. I'll show an example of that later with H-bridges. However, you want to make sure that you don't try and source too much current, or for that matter, sink too much current, because microcontrollers really are not designed to provide you lots and lots of current. They're providing control. So in this case, I think we mentioned this again. If we wanted to, let's see, did I actually cover that, or did I just do the inputs? Yep, we just did the input. So if I want to drive this, what two pieces of code am I going to have to write? Well, I could say port D, because that's what I'm working with. I got to set the data direction register. I'm going to work only with a single bit if I just want to do the very first bit, right?
That must be.
And then B0. And what I'll set this to is, now this 1 right here will be automatically, since it's a constant, will be automatically converted into the correct size, in this case a single bit. Now if I were using variables, I would have to make sure to do my casting. And then if I wanted to wind up this LED, port D dot data register dot, we're doing a single bit, dot B0, and that's going to be equal to, if I want to turn it on, it's going to be 1, 0, which is it? 1. All right. That's because if I want to give it VCC, then I'll have a higher voltage going down to ground, right? You can just as well put an LED the other way. Would this work?
This will work. For logic 0,
Should drive
for
out.
logic 0 it will work.
What should I do with this?
Port D,
These
not
are the
DR,
zero.
zero.
Then it will work.
Logic 0 should be assigned. What's the direction?
Output.
Direction must be 1.
Oh, that makes it a little bit tougher, right?
Direction must be 1.
So for setting the direction,
It is an output, so your direction must be 1.
Should sync correct.
well, that's interesting. So it's going to sync even though you're setting the direction of something. So no, this is nothing good. That's not a good design. All right? So, now that you have those basics under your belt, let's take a look at a little bit more detail with respect to how these ports are going to work. And this is important with respect to some of the old boards or when you're doing coding. Now, you're going to be, you need, question? Oh, okay. You need to be ready for some of this when we start talking about the C programming language. So far you've noticed that we've used port D, DDR, bit B0. Behind the scenes, there's an include file. So behind the scenes, there is an include file. that actually says that port D is memory location 0 hex 0000 103E, I believe. I'll have to check on this again, but I believe this is correct. So what that tells you is that somewhere in RAM memory, it is saying that, I'm sorry, somewhere in the memory of the device, it's saying that the address 00001030 is actually port D. Remember we talked about memory mapped ports. But this would be really difficult if you had to write in that address every single time we used it. So in the include file associated with your specific processor, it will define all of those wonderful ports. Port D, port E, port 4, etc. with a specific address. So that makes life really easy to define in your particular chip. So this is done for each chip. Now what you'll see for each chip is, well, you know, I make that wonderful big board, right? And there's my chip. In this case, it's the RX62N. And let's say physically these are my port D. I'll be hooking it up to a whole bunch of different things, right? And so I will also want to identify a port D as maybe defined as something else. So maybe I really want to say that LED 1 is actually going to be port D .dr .bit .b0. And by the way, if you're writing C code, pound define is a what? What's the term for that? It's a macro, right? It is a C compiler definition. So anytime in your code that it sees LED1, it is going to replace that in your code with physically the word port D.dr.bit.b0. Why would you want to do that? All right, so first of all, so you don't have to write that every single time. Second of all, LED1 is a little bit more understandable than all this other, you know, bit, port, whatever stuff. There's also another reason too. What happens if you change your board a little bit, and now instead of using port D, you're using port E, for example? Can you imagine having to go through every single bit of your code, looking for any instance of port D, and having to change that to port E? That would be a lot of time. So the easy thing is, you build your own include file that is not associated with the processor, but is associated with the board that you're building. In this case, this would be the RX62N, what do we call this? I don't have the board handy with me, so let me see what we call it on. Come on. Hello? Hello? I can't see it on my screen, but I can see it up there. That's interesting. Ooh, I got an email. It is called the development, I can't even read that. Development board, let's just call it development board. Wow, I can't even see that on my screen here. Well, this is not good. Okay, yeah, let's go back to the dot camera, see if we, oh, good, at least we can get this one back. All right, so we have a different include file for the chip, and we have a different include file for the development board. And so don't mix them up or the concept of both. In one, we're making the assumption of, here's how you define port D. This is the chip include. And here, this will be in the board include. And this is one example of using your development environment for actually making life easy. Because now we have LED1 defined up there. And anytime we use it, you can easily identify what are you going to do with respect to LED1, LED2, LED3, etc. So maybe I should back up a little bit and make you do some work. Yeah, I'm going to have you do that. Let's say we have our chip here, and we have port for bit 0 here, and we're going to have this configuration. Switch 1, right? So right now, go ahead and write to me, write the code to do the following. Identify the direction and read the bit and put it into variable my input. Have I done that last class? Did I do that all the way at the end and solve this answer for you? Nope, I didn't. So, what I would like you to do, and it's just a single bit, turn to your neighbor, between the two of you, and go ahead and write 2 lines of code, right? And then I'm going to have 4 of you groups write it up on the chalkboard. Well, I said what's very but you're not working with me. All right? No chalk. No chalk. Well, if you're brave enough, you want to write, you and your buddies write it up on the board? Who's the bold one? For a trip to the prize closet. see, who did I have do it last time? I think I had two guys do it last time. Oh, no, you're different. I'm right up on the board. All right, your turn. You guys manipulate each other, right? You can put your answer up there. Oh, you're still working on it. Okay. You ladies do that? You don't like it? Oh, okay. They didn't do it last time. You did? Okay. You're all separate. You got it?
That's enough. Direct statement.
I don't plan on using the AC button. All right, let's see. Did you guys run anything last time? Last time. Good. I want you to write your solution over on that board. All right, those of you I asked to put it up on the board, please do it. You got it? Oh, they got it. Oh, you got lucky. Where's the Connor, here. All right, let's look at one group who did it. Oh, they even include the word my input. That's pretty good. Oh, are they going back to it? All right, let's go up here. They're working on the DDR. How about this group over here? Oh, they're putting their names up first. And this group here looks like some more people need to work on it, so we'll wait for it for a moment. So I don't see your names up on the board. Same thing all over the place. Tell you what, I have the group up there still figuring out what to do, and actually I don't like any of the solutions I see. Sorry. So I'm just going to put it up, all right? Yeah, I know somebody in the front, you're really eager, but... So, the bit of information that you need is what? Well, first thing you have to do is you have to set the port, right? Well, I said only 2 lines, but sure, you need to set... You need to define the variable, right? So most everybody did that, but you need to set the direction. So port 4 EDR dot bit dot B0 is equal to 0? Ah, it's an input. Right? So then what you need to do is you need to set my input is equal to, remember we're reading a single bit, right? Which means you have to do what with that bit? Cast it into an integer. Port 4 PR bit.b0. That's it. That's all you need to do. So I had some people put some extra stuff up there. First they changed the direction to 1, then to 0. And you folks up there put a while loop in there. That's rather interesting. Okay, so this would be what your solution would be. Now, let's say that we had, I mentioned this earlier, let's say that we had that lovely possibility where we said pound define, and we put pound define switch 1 port 4 dot what? ER dot bit dot B0. By the way, when I do a pound define, do I need to put a semicolon at the end of it? No. So how would that code change if I did that? Well, we still would have to do this line, right? But the only thing that would change is that my input int switch 1. All right? Isn't this fun? You bet. Oh, so my volunteers up there who did the stuff, here's a little bit of swag you could or free stuff. Oh, it includes a squishy thing. Golf tees. This is something that the ladies really like, from what I understand, because you're golfers, right? Yeah. The NASA pin. Neil Armstrong died this weekend. Someone to think about. And oh, look at this. This has flown on the space shuttle. That's what they say on the back of this, and I believe them. So we'll do one for each group. How about that? And you want to come down and get it? You can. First choice. They're running down. Look at that. Now, let's say I had a little bit of code that I wanted to do this, and I'll add some more things. So let's say I want to do the following. Let's say I want to say turn on the LED and turn off the LED at some time. So maybe I'll do a pound define LED on 1, right? And pound define LED off 0. Then I could really, figure out what I'm doing, right? And maybe I want to also do some more pound defines for the switch. So maybe I say switches off. By the way, is C case sensitive? Oh, yes. So if we look at some of the things up here, yeah, with some lowercase characters are probably not too good. So switches off when we read what? Remember, right here? So if the switch is not pressed, what voltage will this read here?
1, 5.
It'll read 1 logical, right?
Yes.
All right. So switches off is 1, and pound define switch is on is going to be 0. So using that data, or using that information, did we identify switch, or did we identify the LED yet? Yeah, we did. So I'll just repeat it here, right? Pound define LED 1. Was it port D? Dot DR dot bit dot 0. D0 or B1? D0, okay. All right, you've done all that? So maybe I should ask the following question. There's another opportunity for you to write something. And so for me, write the code to identify the directions of the LED and switch 1. Read the button. Switch. If pressed, light up the LED. And oh, by the way, do this forever. So, based on all the wonderful information that you have had already, can you do this? So, spend a little bit of time with your next door neighbor, try and figure this out, and give me the answer.
Well, I guess the LED will be.
So who's done? Who wants to write it up on a board? And he was like, heck no. You ready? You want to do it on a board? Oh, go ahead, go over there. Who's lost? Alright, so no looking at this while I do my solution, alright? Let's see if you get it too. If you can, then you get a nice trip to the prize closet. Okay, so the first thing I said is identify the directions of the LED. We already know how to do that, right? You do realize that port 4 is the what? LED or the switch? So that means it's going to be a input, correct? Zero means input, correct?
You mean like V1 0. Zero is the LED. Yeah, that would be output. You say it's 8. Isn't 0?
Ooh, I'm going to put comments on here. Pretty good, huh? You like comments? The answer is yes, you really like comments. Intent. So what is the words to do something forever? While one. That means you will do it forever and ever and ever. Now we've already identified what switch 1, right? So if we say all right, so is what do you have, what I have? It's exactly the same thing except I use the pound defines, all right? Is there an error in this?
Yes.
Okay, what is the error? Ah, notice this comparison. Switch 1 is assigned to switches on. So what you really need to have is, notice I have an extra space in there. That is the #1 software coding bug ever. And in fact, that one coding bug brought down the East Coast telecommunication switches, a whole bunch of years ago. AT&T, there was a piece of code, they put it in the system, they didn't test it out all that well. Because they had an assignment, single equal versus the double equal, it brought down all the major airports on the East Coast, New York Stock Exchange, everything. Just from a single equal sign. So what does that tell you what to do? Test your code, that's right. So, don't forget that. So does this make sense? Notice, if I had pound defined the data direction registers, I could also have added in there the, instead of using the port 0, I could have set something else up to that. Oh, you went back and changed it, huh? He's a proud guy. This is something that you're going to be expected to do lots of in this class, all right? To understand all aspects of this. Notice I'm starting to use macros extensively. Macros make your code more readable, but you have to set it up correctly at the beginning. We've done this for you. The Renaissance board comes with a lot of these macros already set. The pound defines are already done. There's examples of them all throughout the book. All right. More fun than you should be allowed to have. We're going to continue on. So, I guess one question for you is, what else can you do with these? And in the book, I think I'm going to show a picture of it rather than draw it all out. We have an example of an H-bridge. Does any of my robotics students know what an H-bridge does? I hear it.
It drives the motor.
Okay, it drives the motor. So here we go. Here's a situation, or here's an example of an H-bridge. The neat thing is, what you do is you control two of these outputs from a microcontroller. And notice what it does. It drives two transistors. These transistors are going to be the workhorse of driving motors. Forward and backward, on and off. There's your motor. So this is an example of how you don't want your microcontroller to directly drive a motor because it doesn't have enough current to be able to do that. If you do try and do it, typically you end up with a little pile of silicon goo that doesn't work out too much. All right, let's talk about analog. What is the general concept of analog? An analog signal, an analog voltage, what does that mean?
Continuous.
Continuous. So in our case, continuous voltage, continuous voltage. In the simple case, between what? Between 0 and
High.
VCC, your maximum voltage that you're using for your board. Now the maximum voltage you're using for your board may be different than what you're powering your chip. As a designer, you have to understand what it is going to be. But at this point, we'll just say VCC. So what you'll have going into your microcontroller is a single line. It will go into a port. And let's see if I have identified a correct port. I'll just go with this. So you'll have it go into a single port. And what happens inside the processor, let's call this port E bit 0. So what happens inside your processor is that you will sample at a certain frequency. Whatever your code says you're going to sample. And what it will do is it will say, okay, here's my low voltage, here's 0 volts, and here's my high voltage, and that's VCC, and somewhere between here is going to be what I measure. and I'm going to represent that digitally. So imagine this. If you have 0 and 5 volts, and you want to represent this with 2 bits, 2 digital bits. So your digital bits are going to be either 00, 01, 10, or 11. So obviously you want to say that 00 is going to be 0 volts, and 11 is going to be 5 volts, which means that somewhere in the middle, you're going to represent this, and you're going to represent this, which will be somewhere in the middle, right? Exactly where in the middle?
0.67. The 2 points are 0.67.
Well, I hear different things going on. So should I just say, oh, 2 volts and 4 volts, and just say that's good enough? I probably need to be almost exactly in the middle, right? So would this be 1.3 volts? 1.66? And 3.3 volts? Does that seem about right? So that's just about in the middle. Now, can you imagine this? 4, that doesn't do really well, does it? That's not very much resolution. So what you'll often see in your analog to digital conversions with your analog to digital converter is something like 8 bits, or 10 bits, or even 12 bits of precision in the microcontroller itself. Now you could buy some external pieces of hardware that will give even better precision, but when you get above 12 bits, you have to have really good designs of your boards, because that's getting down to noise. But now look at this. How many bits, or what does each 1 bit represent? Well, if you use the really simple concept of your voltage ref positive minus your voltage ref negative, all over 2 to the n bits, that pretty much tells you what your resolution for each single bit is going to be. Well, in this case, our negative voltage, if we declare it in our system up here as 5 volts is the upper end, minus 0 volts is the lower end. Ooh, I hate when that happens. Oh, I can't believe it. My hand turned this thing off. And we're back online. And let's say we're using 10 bits. 2 to the 10. This is going to be equal to 5 volts over 0.024, and this is all equal to, somebody with your calculator, tell me what that is. Can I pull up my cell phone calculator faster? That's all I hear. You got to raise your hand and then speak loudly when I call on you. Yes, ma'am.
4.8 milli.
2.8 milli.
4.8
4.8 millivolts, which is equal to 0.0048 volts. You like that?
No.
You don't? Why not?
Very low.
That was very low. Oh, you don't. You like the calculation? That's okay, right?
Yeah.
Yeah, you just don't like that voltage. But think about this. If you have a moving signal, don't you want it to be as accurate as possible? Possibly, I like that. Well, one example of that could be the temperature in this room, which is at a, I'll tell you what. Oh, it's set at 59. I'm glad it's working. You know what, there's got to be a a way to lower this temperature in this room by turning the lights down. Oh, that helped. That's the problem, is those lights right there are like two big giant heaters. So I'll have to fix that in the future. Here's hoping that the video can pick all this stuff up, but I think that's more interesting than me. So, if you're looking at the temperature, yeah, this is something that's not going to change much, and that will have a resolution that really, it doesn't matter if you're going down to 75.122 degrees, right? Because, it's just temperature for us. But if you want to measure something that's going to be a little bit more precise, a voltage for an accelerometer, for example, a device that will measure how fast you're going, you might need that precision. And in fact, there are some devices whose range is only going to be like 1 millivolt, 0.1 volt or 100 millivolts, right? So there may be a situation where the range of voltages isn't going to change that much, so you need to have some good resolution to be able to pick it up. I said 100 millivolts, I probably meant 1,000 millivolts. No, 100, that's right, the range is 100. So, what I'll say is that, that's a good enough voltage, that's an interesting one. So let's take a look at another one. Another example, right? Let's see. Let's say our Renaissance board runs at 3.3 volts, and there are 8 bits of resolution. So what is the resolution of each bit? So in other words, if I do an A to D conversion, and I have 0, 0, 0, 0, 0, 0, 0, 0 in the first time, that's, I'm assuming 0 volts. Then I do 0, 0, 0, 0, 0, 0, 0, 1. What is that voltage? So do that computation for me right now. Ooh, so fast. Let's get other people to do the computation, and then we'll ask everybody.
Can you lower it?
Say that again? There we go. And so our answer is it going to be 0.01289 volts?
Yes.
That looks good. Oh, so if we have the same board and we use 12 bits, what do we get?
0.0008.
Say that again?
0.0008.
That's pretty darn low, right? So, we will continue this lecture when I come back on Wednesday the 6th, I believe, something like that. Thank you very much.